If you've been following along, it feels like we've been doing endless coordinate transformations, and it turns out we have, but not quite endlessly because we have one more to go, and that is to get from the local frame, and that might be, for example, the normal to a local interface or along the fiber axis where there's some symmetry to simplify the tensor analysis, and to the laboratory frame. And we have to do this because we make experimental measurements in the laboratory frame in terms of defining the polarization states, but what we really care about are the tensor elements relative to the local symmetry axis of the material. And so we have one more coordinate transformation to do in order to describe and connect the laboratory frame polarization state measurements to the local frame tensors. And we will again use Jones tensors to describe all of this. And what do I mean by a Jones tensor? Well, it's just like a Jones matrix, except now it's a 2 by 2 by 2, because there's only horizontal and vertical. So we have 2 axes instead of 3 axes, and that simplifies things quite considerably, because if we have 2 to the 3 instead of 3 to the 3, then we have 8 elements instead of 27 elements to describe our tensor, our rank 3 tensor. And that happens because there is no polarization component for a plane wave along the direction of propagation. So the polarization state is really completely defined by this Jones reference frame for a plane wave. And of course, we detect at the detector something that is a plane wave response. And so we can generate that by doing 2 operations. The first is a rotation, and that rotation operation is, if we go back to the field, if we go back to this illustration, that's going to connect the local frame here to the laboratory frame here. That'll be through some coordinate transformation by rotation, and that's going to be described by that rotation matrix. And then we do one more thing. We simplify the tensor to remove the z component. So every z component is lost by multiplication by this contracted identity matrix. And it's contracted such that it removes the z component, because that's the component along the direction of propagation that can have no polarization dependent information, and that's what reduces the dimensionality down to 8 from 27. So we lump all of these things together into the one matrix we call J, and J converts from the local Cartesian frame, and the effective there indicates that we have yet to include this already includes, my apologies, Fresnel factors for describing the change in local electric field with respect to what we're driving in. And there's another lecture on that, so don't worry too much about that right now. Just bear in mind that this local frame tensor, because of the prime, includes all 27 elements, and so we do an 8 by 27 transformation matrix, which is given by this product to generate the vectorized form of the Jones tensor. And that is so this matrix J is an 8 by 27. All right. So let's look at a simple example of how this works. We'll just consider something actually quite similar to this illustration here, where we have some angle phi between the local z-axis and the laboratory horizontal and vertical axes. Actually, I should have drawn my phi the other way, to find phi with respect to the horizontal axis. And so if phi is defined in that way, then the rotation matrix, if we just take our standard rotation matrix given here and assume that we have a tilt angle theta of 90 degrees and a psi of 0 degrees, and if you're talking about either a fiber or a membrane, then then that value of psi is arbitrary. We'll get the same net result just defined because x and y are equivalent in the local frame. That we'll get what looks like different results, but because of the equivalency of x and y, they will actually be degenerate. So if we do this operation, then here's our little I, this contracted identity matrix, and then we plug in the rotation, the angles, and pull out the rotation matrix for projection, and this is what we get. And so this product yields this 2 by 3 matrix. Now, if we assume we have local uniaxial symmetry, then it turns out there's a whole massive reduction. And of course, this goes back to the discussion previously on symmetry and character tables. But we can pull out and significantly reduce the local frame tensor elements to just 4 unique values. In the case of something that is a chiral assembly. If it's an achiral assembly, then there's only 3 unique values. So there's 27 possible, and I'll go through this quickly because this is really the topic of a different lecture. We can, if we have local uniaxial assembly, a uniaxial symmetry, these are the full set of all non-zero tensor elements, and of course we can relate those back to the 4 unique ones through a symmetry matrix Q. And how do we populate that symmetry matrix? Well, this is we can use ternary counting again to help populate that, and that's what these are the elements that we get. For the chiral elements, you'll notice there's a sign change along some of them, but this set describes the achiral components, and that fully populates the set of all 27 elements from the much smaller set of 3 or 4 unique elements, depending on the chirality in the assembly. Now we can go back and take this Q and multiply it by this Kronecker product of this 8x27 matrix, because Q is a 27 by 4. So we have basically an 8x27 times 27 by 4. Sorry about my handwriting there. So we'll end up with obviously an 8x4 product when we include this rotation operation with that symmetry matrix, and that's this 8x4 matrix right here. If we only have rotation and phi, then we only have one angle to contend with. Now, all of the architecture we have built up has been focused on interpreting the molecular nonlinear optical properties in terms of this effective tensor element. And what we're going to show and measure experimentally in the laboratory frame is the Jones tensor element. So how do we take measurements of this and extract these local frame tensor elements? The way you do it is just by inverting. You've got an 8x4 matrix connecting the two. So if you left multiply by its transpose and then left multiply again by the inverse of that product, you then, this is standard linear algebra manipulations, you can then isolate the effective and write that in terms of what you measure experimentally in terms of the Jones. Now if we extend this, make it more general, if we still assume that we have uniaxial but now allow both azimuthal rotation and in-plane tilt relative to the field of view, and that might be, for example, in a collagen fiber where the fiber is not necessarily lying co-parallel within the plane of the field of view, but can be oriented into or out of that plane as well, then all we have to do is simply add in a theta dependence in addition to our phi dependence. And we do that by just throwing in another number or another letter. And this time we're using capital letters to indicate the theta dependence and lowercase letters to indicate the phi dependence. And this 4x8 matrix, 8x4 matrix has this form at the end of the day. And that takes us to the point where we can start thinking about the next steps.